titled Solutions for Combustion Control in High Particulate Applications. I'm happy to get us started and highlight just some important things that I think is interesting to think about. How do we think about high particulate applications? What's the great extent to serving these applications? So let's get us started. So let's jump right into the agenda. So as I said, the purpose of today's webinar is really to simplify the added complexities of flue gas analysis in high particulate processes. So what we'll do, we'll start by jumping right into some of the primary drivers. Why do we even think about flue gas analysis in high particulate applications? Why would operators even want to care about that? We'll also talk about the first line of defense for an analyzer. So what's the first thing? If you have any little bit of particulate, what's the first thing to think about? And then at some point, okay, what other things do you need to think about in the analyzer as you can get confronted with more and more level of particulate? We'll also talk about some proven installation techniques that are useful, especially for making sure that there's a representative sample. And we'll also talk about some additional considerations for safety, especially before a baghouse or electrostatic electrostatic precipitator. As I said, I'll be monitoring the chat, so if you have any questions, feel free to message them in the chat. And otherwise, we'll also have time at the end for questions. So let's get started. So the first question related to the drivers of flue gas analysis, why even monitor the flue gas? And so the first thing to really think about is combustion requires oxygen, fuel, and heat. I mean, that's something that's inherent in the fire triangle. And with that in mind, there is some amount of incomplete combustion. And that creates what we call combustibles. So if you can kind of see in this generic reaction with methane, oxygen and methane first generate partial oxidation. So they first generate carbon monoxide and hydrogen. And then if any additional oxygen is available, then they further oxidize to create carbon dioxide and water. So this intermediate step of combustibles, can come from a number of places, including just the natural poor air to fuel mixing at the burner. So not all the air is mixed perfectly in proportion with all the fuel. You have greater pockets of fuel and air at different places, and that anomalous combination can result in higher levels of combustibles, especially with poor mixing. Also with variable loads and changing conditions, it's very possible that you could go from one fuel source to another fuel source. You could go from operating with methane to operating with a high hydrogen fuel. That'll change the reaction in the process at the burner. As a result, that may create a pocket that creates combustibles. So small amounts of incomplete combustion. And it's normal to have ppm levels of incomplete combustion in any type of combustion reaction. It's the concern becomes higher and higher levels as you get closer to percent levels. And then when it comes from like a flue gas analyzer perspective, the relevant measurements that I really see is the oxygen measurement, as you can see here. So not the oxygen coming in, but actually the oxygen on the outlet. So what's the excess oxygen after the reaction is complete? What are the combustibles? What's the combustible levels to monitor for the intermediate health of the process? And then also, what about fuel? What about any unburnt fuel that went along? Can we monitor for that? And then as far as making sure that you have a representative sample, I'd also say sample flow as well as a relevant measurement. So let's dive a little bit deeper into this. So why would somebody want to monitor flue gas analysis in a high particulate application? Well, it comes down to really three areas. The first area is the role of the operational set point. With simply an excess oxygen measurement by itself, after all combustible compounds are consumed on this sensor, you have a direct correlation between the air and the fuel ratio. You can correlate the excess air at the burner with the excess oxygen in the flue gas. And so that rule of measuring excess oxygen provides a means of ensuring that you have sufficient air, combustion air, at the burner with enough safety margin in case there is process variability or fuel source variability. And for some industries, like the lime industry, the operational set point is important so that you can maintain product quality. So there's even an overlap into product quality when you look at an operational set point. Even if you think about like a steam methane reformer, you still need to set it at a certain level so that it's not too hot for the tubes, but also not too low where it's creating a low yield scenario. So in all those cases, it's important to make sure that you have an operational set point. In a lot of cases, that plays into the product quality. So the first reason why a operator would want to measure flue gas analysis in a high particulate application would be to have that set point to make sure that you have sufficient air to fuel at the burner and subsequently adequate product quality should your process require some type of um, precise oxygen measurement or precise combustion control for the product quality. The second is the role of efficiency and optimization. So by monitoring combustibles or the forms of incomplete combustion of carbon monoxide and hydrogen, you can really monitor for the health of the process. And as a result, you have a secondary reference point for the optimum amount of excess air. Now, I won't go too much into that in this presentation. I have certainly a number of other presentations that you could view and other webinars that you can view that talk about optimized combustion and combustion optimization. But really, the main reason why somebody in a high particulate application would consider a combustible measurement would be for the role of optimization and for efficiency. As you lower to a more optimal excess air set point, you also reduce your CO2 and NOx emissions and generate a cost savings by reducing your fuel consumption. So there's a direct return on investment, both on the environmental side as well as on the financial consumable fuel gas side of things. Now, the third reason why an operator would even consider flue gas analysis is the role of safety. And safety is probably the most important one, but just to give it emphasis, I mentioned safety margin up here at the burner. That's certainly important to make sure that you're above stoichiometric conditions, make sure you're above fuel-rich conditions. But also, by measuring for combustibles, you can alert for incomplete combustion, making sure that there's no no high levels of combustibles reaching combustible breakthrough, things that would be concerning that would suggest that you need to take a look at the heater or you need to take a look at the boiler. So the first rule is just monitoring for combustibles breakthrough for ppm levels of measurements of combustibles. And really the second other reason is also by monitoring and detecting percent levels of hydrogen and hydrocarbons that may be a result of fuel leaks or some type of loss of flame scenario. So why would an end user look at a flue gas analysis for their process? For one of these three rules or for all of them? For operational set point for quality, for optimization for efficiency, or for the insurance of safety to equipment and to people. So as we go back to the fire triangle and just thinking about why operators even think about flue gas analysis, it really comes down to excess oxygen being that combustion control set point for air to fuel ratio and for process integrity for product quality. For combustibles, it comes down to monitoring for safety for combustible breakthrough, but also for burner optimization to reduce the fuel consumption. And then also for methane and hydrocarbons to monitor for safety to detect flame out or gas leaks at the burner or during startup or light off conditions or purging cycles. And also from a combustion flue gas analyzer perspective, also sample flow, making sure that you have a confirmation that the sample is representative of the process and is in the right range. So, and that the process and that the analyzer itself is not plugged for whatever reason. So from a high level, as we just look at combustion, get started into this webinar, I really want to make sure that we're reminded that every measurement has an important role that plays into the overall picture of the visibility of the health of the combustion process. So now all of these measurements are interesting, and all of these measurements, specifically the oxygen measurement, can be translated into different forms. And so that's where I'm going to go into this next topic. So these are the 4 key zirconium oxide analyzer types that support combustion control. And they all have their different advantages and capabilities. And we're going to talk about each of these and how these play into our decision on the high particulate application. But before we go there, after I just introduced that this is the 4 different types of analyzers for combustion control, I did ask the question, what is the first line of defense? And I propose to you that the first line of defense for any of these analyzers is actually the consideration of a filter. Filters are really the first, if there's a hunch that there could be some type of particulate in the atmosphere, we first think about the filter. So when I talk about filter, a filter can be used on any one of these types of analyzers. It can be used on an in situ analyzer that's mounted to the process flange and the zirconium oxide cell is in the process. It could be in a closed coupled extractive design, mounted on the back of the probe. It could be mounted in a convective cell, back on the back of the probe there. And it can also be as part of a sample conditioning system for an extractive analyzer. So all of these analyzers can really leverage a filter for high particulate, and that's why that's really the first line of defense in any potential high particulate or even low particulate application. And just so you can get a flavor for what these look like, this is an example of some of the W5 filters and some of the filters for close coupled extractive analyzers, where there are different where they attach the back of the probe, but there's different flavors. So you have the ceramic filter for higher temperatures with certain adapters, whereas there's also have a stainless steel filter with a deflector shield here that all protect the probe and the process and the filter from the process. So other things to think about, really the form and the function of these filters vary across the analyzer types. So if we look at the in situ type, for example, like this, this is an example of what our oxygen sensor looks like. It's actually inside this type of this little metal enclosure, but still exposed to the process with a screen on the back of it. But if you were to add a filter, there's certainly a stainless steel filter that would support the diffusion flow through to make contact with the zirconium oxide cell. There would be the ceramic filter as well that could attach for higher temperatures. So the form and function really vary based off of the analyzer type and also the application as well. And then if you look at more like application-specific attachments, this is an example of our convective type analyzer where it has an inner outer probe design. In this particular case, it's a ceramic probe and filter design. And some of the additional attachments might be this perforated sheath, for example, which is kind of closed off on one side, but allows the process to flow without building up particulate directly on the process flow, directly on the filter as the process flows by. So there's a question about how do you clean the filter, flow back or change. That's a great question. There's different ways to change the filter. The first thing is accessing the filter. So there's two ways to do it, and really what our service team typically recommends is if you had a spare filter, you could, if you detected some type of plugging event, you could actually pull the filter out of the analyzer. It really depends on the type, but really you could pull the analyzer out. You could pull the probe and filter out. You can you could remove any plugging within the actual probe itself, and change the filter, remove the filter, put in the new filter, put it back on process. And then with the other filter, you could just put it in vinegar and let it soak. Tends to be one of the good solutions that we've seen. There's other solutions too that you could use depending on maybe depending on the type of process itself. But having two filters is one quick and easy way to change the filter and keep you up and running on the process. So, but typically you could just submerge it in a solution and it'll actually help remove off any of the particulate so that you can reuse it in the future and then use it as part of the cycle. Okay, so that's just an example of, so just going back to this example, this is some application-specific attachments that could be used. In this case, if you had some type of abrasive material or some type of really like sandy type material, you could, in high particulate, you could actually prevent it from plugging by having the perforations on the back and on the front, so that anything that would hit the analyzer would hit the filter would not directly affect and plug up on that side. Okay, so just another example from the convective analyzer type. And if I were to just summarize it, if for thinking about a filter, it comes down to a few things, but they're important things to think about. You may or may not know, but if you have some sense for what the particulate size is, that is certainly one of the things that we think about. So there are different filter options for 5 micron particulates, for 20 micron, for 30 micron. And if you have a sense that it's very fine, you could opt for the 5 micron, or if you think it's a bigger, more coarse particulate, you could go for the 20 or 30 micron filter sizes. So that's the first thing I think about is the porosity. What's the particulate size? The next thing I think about is really the process temperature. Uh, the temperature will directly impact the material that you choose. So there are sintered metals like 316 stainless steel, 310 stainless steel. There's even hexalloy probes and other ceramic type materials that can be used for higher and higher temperatures. And so those those materials apply to the actual filter itself and what options are available for those high temperatures. But they also apply to the bushing material too, making sure that the metals in contact, the attachments onto the filter actually can withstand the high temperatures. So it's both the consideration for the bushing material as much as it is for the probe for the filter material. Excuse me, the filter material itself. And other things like I alluded to is really the attachments. Based off the nature of the process, we can understand, does it need a deflector shield? Does it need a removable sheath? Does it need a perforated sheath? Does it need something to be attached to it to protect it? Like we even have armored shields too for really harsh environments. All of these things in mind, they protect the filter, but also ensure that there's enough sample flowing to the filter for making the measurement in the analyzer. And so this is an example of a deflector shield that would go on to sort of an in situ type that would slide onto that. This is an example, like I showed you before, of a removable perforated sheath type attachment on the filter. And then these are just some of the filters that you can see. This is a metal filter, and this is a ceramic filter. So simple, but also important things to think about depending on your process. So now I want to take a step back and look at some of the analyzer types and how the analyzer types really play into the configuration that you select for the purpose of the process. So selecting the analyzer depends on the application. And so we have 4 different types, very important and very similar and very different. How do we think about that? So I figured I'd give you a matrix to think about when would each analyzer type be relevant. Now, certainly the fastest response and the most capable of measurements is the close couple extractive type, similar to the WG5 or the WG4 analyzer, if you're familiar with those types. Close couple extractive, that's suitable for up to 1600 degrees Celsius, so very high temperatures. That's up to 3000 degrees Fahrenheit. It's capable of 4 measurements that I mentioned. It's capable of oxygen, combustibles, methane, and flow. But it can only handle lower particulate loads. With a filter, it can handle minimal amounts. It can handle some. That you certainly want to be. We would monitor flow to determine if we need to change the filter. We also have a blowback version that can handle more. That can handle more particulate, but it's still within a certain range. So if you're looking for the fastest, but the least amount of particulate, close couple extractive (CCX), close couple extractive would be the recommendation. If you start to have higher and higher levels of particulate, more sticky particulate, like the second fastest would be the convective type, which would be suitable for up to 1500, a little bit over 1500 degrees Celsius, like 2800 degrees Fahrenheit. In this case, it's capable of oxygen, combustibles, and methane measurements, but flow is not as easy to measure with the slower convective forces of a convective design. Now, that being said, it has been proven and capable in high particulate, sticky particulate, dusty applications. So it can really handle the full range of high particulate within the constraints of different processes that we've seen. Now, as far as the next fastest or the slowest, so as we get slower down, as we go down this list, as we go slower to the more the in-situ type, as we think about that one, that's also capable of handling higher levels of particulate. I wouldn't necessarily say sticky particulate, but higher levels of particulate. but that's only able to measure oxygen. So it's only able to make a single measurement, and that's actually limited to the temperature that can be reached at less than 670 degrees Fahrenheit or Celsius, 670 degrees Celsius. So that's also limited on temperature. So you have this balancing of what are you looking to measure? Are you looking for optimization and additional safety with combustible methane, or are you simply looking for an oxygen measurement in high particulate loads? And then finally is the extractive type. Now the extractive type is versatile because the analyzer does not depend on its interaction with the process. An extractive analyzer depends largely on the sample system. So you could have a water-cooled probe that can handle very high temperatures. You could have a water wash probe that could handle very sticky particulate, or very acidic environments. Now that being the case, from the zirconium oxide perspective, those are still only able to measure oxygen, but they, depending on the sample system, they could have much far-reaching capabilities as far as what probe that you choose to put the back end of that sample system. So just as a quick picture, some things to think about if you're looking for like lower loads versus more measurements versus higher temperatures and higher loads versus less measurements. So when it goes to even higher and higher measurements, I know I mentioned convective analyzer, but I do want to highlight that as well as the close couple extractive type with blowback. Now, when we talk about blowback, that means that there is a puff or a blowback of of high pressure air and to blow off particulate on the filter in the probe. I'll show you some examples in just a moment, but that's the purpose of a blowback analyzer, is to provide a first defense to puff off and blow off any type of accumulation on the probe and filter. Now, because it's high pressure air forced through a tube, there is a limitation on the probe and filter length. And so what we've seen with our blowback type analyzer is that it really maxed out at about 8 feet. After 8 feet of combined length, you could still probably do a blowback, but it wouldn't have the same power and strength and pressure to blow off the filter as it would at a lower length. And really for the blowback, because you're putting high pressure air through the probe and filter, that really works for dusty particulate that can be just puffed off. And we've seen it can work pretty well in applications with less than 30 grams per meter cubed of particulate loading. So that's how we think about it for a blowback analyzer, and I'll show you more pictures on that in just a moment. But before that, as I contrast that, I would like to also highlight the convective analyzer type, which uses convection, which is a slower force compared to aspiration. In this case, close couple extractive has an aspirator. In the convective type, it's a slower flow sample flow. Now that being said, it's limited to an even smaller length of 4 feet because that convective force is only so strong, and while it slows the flow, it also slows the ability to pull a sample at greater lengths. So that is limited to probe length, but that is suitable and proven in high particulate applications and sticky applications, and even we've seen in even saturated environments as well. So as I go more into each of these, let's talk about the blowback first. Now, an example of a blowback analyzer would be sort of like this, where you see a massive accumulator ball in the back, and that accumulator ball holds high pressure air, typically above 80 psig, and that high pressure air is heated with a heater, so it's maintained at high temperatures. And what it does is, when it's time to initiate a blowback, whether that's automated or manual or timed or based off of a percent of flow, once there's an indication to do blowback, this three-way valve protects the analyzer from the high pressure air. And so the three-way valve initiates, and as that three-way valve initiates, the high pressure heated air forces through the system and out to blow off the probe and filter. And specifically, the one in this case, it actually uses a pulsing action where it does a big puff and then it pulsed. Then it does another big puff and then it pulsed. And that pulsing effect provides a almost like a vibration that would otherwise hit differently on the filter to blow off any type of dust. So really important to a few elements, but very important. How would you access it? Well, this is one way you would access the probe and filter by taking it through this path, removing this probe connection, and taking off this little hook right here, and making sure that everything remains within the correct temperature levels. So this is an example of the blowback, and if you want to see it in real life, you can see that this is the blowback. So here's the three-way valve here, the high pressure air. Again, it's heated so that nothing can condense within the line. So the hot air can vaporize any type of water condensation that may accumulate, or to prevent any accumulation of condensation because of cold air. We don't want a high pressure cold air. So as you have high pressure heated air, three-way valve lets it go and goes through the hook and out through the process and out through the filter. So that's what you can see, and then the return of the analyzer goes through this and then back to process. And then underneath, you can see there's also a pneumatic actuator. That actuator is what drives the three-way valve. And then you can also see it's a little hard to see, but if you were to attempt to install the probe, it would be with a special tool, installation tool, to help you get a grip onto the back of the probe to pull out the probe and filter. Okay, and then this is just an example with the cap remove as it was accessing the probe and filter at this time. So you can kind of see it on the process. Now, shifting gears a little bit, going from blowback close-coupled extractive analyzer type to a convective analyzer, you'll see some similarities to close-coupled extractive and also some differences. Now, if you just examine it real quick, you'll see that there is no aspirator in this case. So it's not aspirated. It's actually drawn based off of multiple forces, including the diffusion into the filter, but also the convective force of the high temperature of this furnace. This high temperature furnace actually creates a convective force that pulls the sample through, up, in contact with any combustible detector, any methane detector, through the oxygen analyzer, and then back in return. So just a little overview that you can see there. And if you were to trace back to its roots, the convective analyzer is actually a combination of the elements of an in situ and a close-coupled extractive. I alluded to this in the beginning, but what you can see is that it brings the concept of diffusion through the filter, like it would be in an in situ, with some of the advantages of a close-coupled extractive design. Certainly you don't have the aspirator, but you still have it close coupled on the process flange, the capability of additional measurements in the high temperature furnace that creates a convective force. So just like it does in a close coupled extractive, creates a convective force, it also does so in a convective type. And so the convective type brings all those advantages together into one unique high particulate analyzer. And then again, this is just you can see it in all the combinations. You can see how it would mount onto the process flange. You can see how there's the diffusion forces through the filters. There's additional measurements in how it has that convection with the high temperature furnace. And just you can see an example of what one of our convective analyzer looks like. You can see here's the manifold block. You can see that makes the right turn up here in contact with combustible detector before it goes to the furnace and then back through the outer annular gap back to process. So it's this is our older version, but it's also just helpful from a depiction standpoint of seeing all the elements in one place. And then if you were to look at our different generations, so this would be a liftoff version of our one of our high particulate convective analyzers on the process versus our more new version with same principal technology, but mounted on the process. So now I'd like to go switch gears. So those are some of the practical configurations for an analyzer in a high particulate case. How do you choose the analyzer? Well, it really depends on the particular loading, depends on what measurements you want to make. It also depends on if it's sticky or abrasive, or if it's saturated, or any of those considerations. After you choose the analyzer, well, how do you mount it? What are some proven installations that reduce maintenance? So there are three that I'd like to share. three different methods for mounting flue gas analyzers, specifically in high particulate applications. The first one is direct measurements. Now, if you take a lime kiln, for example, this is just a nice way to see it all in one place. But if you were to take a lime kiln, for example, you can make a direct measurement with an in situ type going right into the process with the zirconium oxide at the end with the filter. You could also have it behind the seal or right behind the seal, but these are mounted directly to the process, getting the full force of high particulate. And there's obviously different ways to do it, especially with respect to a kiln. You would have like a long probe into the kiln before the seal, or you could have it after the seal in a floor mount or in a wall mount type design. So when you think about direct measurements, they are certainly the most representative of the process because they reduce the potential for any pretend air to leak in to the into the process. However, they're also limited because you could have very high temperatures. So a in situ type will only work for certain high temperatures. There may be access points that are very difficult. The process may be so hot that you may have to remote electronics. So those are all things to think about for high particulate hot applications mounted directly to the process. Typically, the ideal case would be if you want to have a direct measurement on a high particulate application, ideally it would be at a lower temperature, preferably dry application. Okay, so I see that there's a question in the chat related to one of our convective analyzers. I'll revisit that at the end, but that's a good question related to the inside and outside filter. I'll show you at the end though, just so we can go through some of the slides. So that's the first mounting site is the direct measurements. So the next one would be sample conditioning systems, and you can kind of see that right here where there's a sample conditioning system. Now in those cases, this could be like a water wash probe, where it's a very high temperature. You want to cool it down, but you also want to keep it clean from any particulate. A water wash probe would be one example of a sampling conditioning system for this application. So sample conditioning systems for high particulate, they could be water washed, they could be water cooled. They could handle even acidic conditions and very harsh conditions. Now it's separate from the analyzer though, and because it's a separate system and with its own complexity, it can be certainly damaged or from process opposite conditions or from frequent calibrations because of just the design of the sample conditioning system. Now that being said, though, the sample conditioning system does reduce the complexity of the analyzer selection. It makes the whole system more complicated, but choosing the analyzer can actually be more simple. It could be simpler. And for that, you can choose an extractive type to measure oxygen. And there may be ways to take a heated sample line and a sample conditioning system and even draw it up to a close coupled extractive type in case you were looking for all four measurements. Now you'd have to tie in all of the appropriate aspiration so that the aspirator is working at the right pace, but it does reduce the complexity of the analyzer. Extracting analyzers are much more, are generally a little bit more simply designed compared to a close coupled extractive type design. So that's just a perspective on sample conditioning systems. And now the last type, the bypass system. There are some bypass systems that we found to be pretty effective and successful in high particulate applications, and that's something I want to share with you. They've really proven themselves across industries. And so the first one I'd like to highlight is that of the vertical probe. So the vertical probe design is if you had a kiln, for example, like we showed you before, this keeps all the dust flow in a downward position. So even though a sample fan is pulling a draft and the sample flow is going this way, you could actually reduce particulate buildup because it would all be falling out because of gravity. So generally easier to maintain. It's easier to maintain the analyzer in this type of case. So really the best recommendation is to locate the analyzer at a suitable point in the bypass. So as you create a bypass, I've seen these on cement kilns in multiple different applications in different ways and shapes and sizes. But really, whatever becomes that suitable bypass design for your footprint can certainly make can provide a representative sample, but also an easier to maintain analyzer, less prone to overheating or anything like that because of high temperatures. That's the first example, and this would be a lot easier to maintain compared to something that may directly see the brute force of all particulate. Now, the next example would be a bypass measurement using a horizontal probe. So in this case, as you can kind of see in this picture over here, horizontal pipe. There's a fan at the very back pulling in the sample, and yet there is a turn. You have the sample flow going through. You'd have a buildup of particulate at this little leg right here, at this little Y point, but that could easily be blown off manually with high pressure air uh, in a less sophisticated way to blow off the particulate back into the kiln. You can then make the measurement for the analyzer at this little horizontal probe point, and then again the induced draft fan pulls it so that you can bring it back to a lower pressure point downstream to maintain the flow. Finally, would be the final example of a bypass measurement system would also be that of a sample box or a knockout box. Now, this is in the case of like you have a physical box, so not like a probe or tubing, like something like that, but actually like a physical dropout box. This would be example one. I'll give you another example again, where the bypass sample box, it collects the particulate, and it uses the same principle of pressure differential that allows some of the flow to go through this bypass and out to a lower pressure zone downstream. Sometimes there could be a fan downstream or multiple cleaning points, something like that. But it's a lot easier to maintain. You don't have all the flow directly impacting the, the flow with all the high particulate impacting the analyzer. You have some place for it to drop out. And so in this case, the pipes can be cleaned. You can see there's multiple cleaning access points. It says from the design of this sort of sample box, knockout box. Now, to give you an example of one in particular that is interesting to share is if you can kind of see here, this is an example of a bypass system, a knockout box on a kiln, and you can see that there is the convective analyzer here. You see the convective analyzer over here. You can see the knockout box right here. You can see the intake from the kiln right here. And so what happens is there's a fan at the end of this pipe right here, and that's pulling the sample. That you can actually see right here. There's the fan. There's actually multiple fans. There's a fan over there too for multiple bypasses. But that being said, the fans are nice because they pull the sample, overcome the force of the the kiln, and they allow a dropout spot for the particulate and even a blow off section. I'll show you the blow off section in just a second. So just to give an example, so from here you could the induced draft fan, as I was saying, is pulling the sample, so it pulls in right from the kiln. There's this little blow off section here, so if a particulate were to accumulate, you can actually blow it off or use high pressure air or knock it out. That diverts into what we see as the knockout box right here before the measurements are made by, in this case, both analyzers, and then taken downstream to return back to process later on downstream. So you really can leverage a bypass system in a knockout box to make a representative measurement, but also reduce the maintenance for the process. So this would certainly plug less often compared to something directly mounted to the process, especially we're even at risk of burning up the electronics close to the kiln or remoting the electronics for the kiln. So just to bring it all together, so when we look at the bypass system, it really provides a reduced potential for plugging, for particulate to build up on the filter. Now the filter will eventually plug up. It does have a convective force that will accumulate the particulate over time, but it certainly reduces the potential for plugging. And it also still requires regular maintenance to keep clean. But because you've designed it the way that works best for your process, that knockout drum can be easier to access with the right access points, with the right blow-off points for your technician team and their support. So we're getting closer to the end. I did allude to, what are some added considerations for safety. So now with all this in mind, okay, from the bypass and from the analyzer, okay, great. When we bring it all together, what are some last minute considerations for added safety? And I had referenced earlier about electrostatic precipitators and baghouses. I do want to highlight something for electrostatic precipitator protection. Most fired equipment, even kilns or even boilers, they start with natural gas as the firing fuel. And with a combustible measurement by itself, that can warn operators about potential issues of incomplete combustion during normal operation. A high alarm of a 0.8% combustibles was rather high, but that could provide a set point prior to the precipitator to notify a shutdown for potential unsafe conditions. The nuance is that combustible detectors the catalytic detectors themselves are typically not designed to measure methane. So if you had a fuel leak or something like that at a higher percent level, you may not be able to detect that. And I know with our combustible detectors, they're capable of carbon monoxide and hydrogen. They're very well designed for that range. But when you start to look at methane, it doesn't operate hot enough to correct methane. Methane is an additional measurement. So when you think about measuring for methane during light off and for purge cycles, that's really where high levels of methane could be leaked from a burner, especially during startup, that could cause a hazardous event. So a precaution would be to have the additional assurance and insurance of having an analyzer with a methane detector, so that you can monitor for potential fuel leaks during startup and purge cycles, but also have the monitoring of incomplete combustion during normal operation. So really, I mentioned those four important critical measurements. It really comes down to the full visibility of the combustion process to ensure that there's safety during startup and normal operation. So mentioned before, but just reiterating it again, the importance of having the full visibility of the combustion process. So now I do want to put in a little pitch just towards the end. Recently, we released a new product, specifically the newest version of our convective analyzer, the Thermox WG5 HP analyzer, building off of the proven capabilities of its predecessor, the WDG HP2 analyzer. And so just quick highlights. And if you have one of these in your process, this might be really relevant to you. So I just want to quick highlight. After we talked all about convective analyzers, this specific design has improved serviceability, a lot easier to access these 4 bolts for removing this entire internals from the process. So customers who may have pulled the entire analyzer off the process to access the probe and filter no longer have to do that. And I know there was a question earlier about like the vent goes, where's the probe and filter go? So in this particular analyzer design, you would be able to pull off this entire internal piece and clean off the probe and filter that way, leaving the entire rest of the analyzer enclosure mounted to the process. As far as the other things to think about, there's greater combustible stability. There's a bigger thermal mass for the combustible block. That's a lot easier to change the detectors with the WG5 style detectors with just a hex screw on both sides. So easier to maintain there, and bigger thermal mass to maintain the temperature of the combustible stability. It also has the digital diagnostics. It has the electronics of the WG5, so able to work for an HMI, able to work with TCP/IP with Modbus capability, and it also has a pretty useful predictive diagnostic that leverages the essentials of artificial intelligence to determine detector end of life. So all those things pulled together, it's certainly a new release that is certified for Class 1 Div 2, Class 2 Div 2, ATEX Zone 2, and ICX Zone 2. So something that we wanted to highlight that is a new release, and also in the spirit of convective analyzers, this is certainly available. Should anybody be interested, feel free to reach out. Now, with that being said, what are some of the takeaways from our discussion today? I know we talked about a lot, and I know we are kind of getting closer towards the end of time. We'll certainly have time for questions at the end. Some key takeaways include filters. Filters are by far the first line of defense in a high particulate application. Any of the analyzers that I showed you today could have a filter in some way, shape, or form to support a high particulate application. But we do have to be conscious of potential pore size, the temperature of the process, so what material selection we choose for the filter itself and for the bushing, and for any of the other attachments that we need to support for abrasion or for dust or for high coarse levels or even acidity. So that's something to think about. As far as the analyzer selection, it really depends on the process temperature, the particulate loading, which measurements you're looking to make. Those all play into which analyzer, and that's why I gave you that little matrix so that you could think about when to choose which. And certainly when you get into the even harsher applications, even higher, more severe applications, higher particulate levels, that's where there's a choice between blowback analyzers for more dusty applications, less than 30 grams per meter cubed, versus a convective analyzer, which can handle sticky and even heavier particulate loads. And then as far as a installation style, really the bypass system has been something that has proven itself over time to improve the ease of maintenance and access of the analyzer and the probe, but also to reduce the potential for potential plugging and direct caking onto the filter itself. It does provide at least a dropout mechanism for reducing that. And then finally, for ensuring downstream equipment has the integrity and the monitoring that it needs, having a methane detector having a methane detector on an analyzer prior to electrostatic precipitator is important, or a baghouse, to make sure that you monitor for any potential fuel rich conditions, any potential unsafe conditions during light up and purge cycles. All right, so with that, feel free to keep in touch and reach out to me if you have any specific questions. I will open it up to questions, and I do see we have a couple already. I see that we have a question related to refinery fluidized catalytic crackers and their flue gas processes. Certainly a harsh and difficult application. That's something where we've experimented with variations of the convective side just to support FCC U processes, but that's something that we can certainly evaluate on a case-by-case basis. If you'd like to reach out to me directly, I would initially be inclined to say that a convective type analyzer would be better for this. There are certain applications like continuous catalytic cracking where we don't have a filter and instead we use an exhaust tube. So that's something that doesn't reduce the potential for plugging, but it does reduce the potential of fouling at the end from the catalyst fines. So that is something that we would look at. But feel free to reach out to me with more of the details on your specific process for your fluid catalytic cracker, and we can talk about what are the particular loadings and the temperatures and the measurements you want to make for that evaluation. There was also a question earlier about receiving a copy of this presentation. If you are interested in a copy of this presentation, reach out to me directly, and I'll send you a PDF version. Otherwise, this will be posted on YouTube, so you'll have the slides on demand that way as well. And as far as the question earlier about the filter inside and out and drawings available, there are drawings available. Again, reach out to me. I'll just put my contact information again. Reach out to me, and we can provide you with some of the drawings and show you how the convective type of analyzer uses a concentric inner-outer probe designed to handle this type of process. And while I wait for any other questions, I'll go back some slides and see if I can show you just a sample of how it would work. Yeah, so if you can kind of see here with the inner-outer probe design, you'll see that the inner probe connects right to the back of this manifold block here, as well as the outer probe. And you can see that there's a concentric. So this is the inner probe inside the filter, and the outer probe kind of outer annulus sort of vents out to the atmosphere from that perspective. So it's a unique inner outer probe design, and some of the nuances of itself actually plays into the speed of response based off of like the pitot tube effect and the difference of pressure and velocity. But if you can kind of see here, you can see that there's an inner outer probe design, and that the inner probe is inside the outer probe, and the filter's at the back of that. And yeah. Yeah. And yeah, as far as mixing between, so as far as any potential concerns of mixing, that's not something that we've directly seen. There is, perforations on both the inner and outer probe to so that it won't come into direct contact as much. But I certainly understand the concerns of potential mixing. That's not something that we've seen as a concern since we've had this design for over 30 years. But I definitely appreciate the question. All of our convective analyzers have some probe and filter combination, so it is important to realize that the convective analyzer certainly has a probe and filter. And part of the reason why it doesn't mix as much is partially because of like the pressure differences. That's something else that we've seen. Okay. So as I get back to our presentation, I'd just like to thank you for your time. And if you have any other questions for me, feel free to reach out to me. With that, I thank you and wish you a good rest of your day. Again, feel free to reach out to me if you have any other questions.